Hi, welcome back. In today's video, we're going to be talking about the representation of data, and more specifically, how a computer is going to represent that data. Because at the end of the day, the only resources our computers really has is electricity. We either plug them in or we charge the battery. Alright, so the question really is, how does a computer use electricity to represent data? Now, you may or may not have heard that computers only understand binary. And you already know binary to some degree, even if you don't think so. But binary is just a way of counting, and we know how to count as humans. So us humans typically use what's called the decimal system, dec implying 10, and that's just a fancy way of saying that we count using 10 digits, 0 through 9. But why is that? Well, it's convenient for us because we have 10 fingers, 10 toes, and with the decimal system we can count as high as we want. Because once we get to 9, what do? We switch it back to a 0 and we give ourselves another digit. The same can be said with any other quote-unquote base system. Decimal is technically just base 10, and we'll see why that's the case in just a minute. So how does that apply to binary? Well, binary is just a system of counting. Bi implies 2 digits, and this is just a fancy way of saying that we count in binary using 2 digits, 0 and 1. Now, why is that relevant to computers? Well, because at the end of the day, computers only have access to electricity. The computer can either choose not to store some electricity, essentially representing a 0, or it can choose to represent it can choose to store some electricity, representing a 1. Okay, so let's get into an example. How would we represent the decimal number we know as 0 in binary? Well, simple. We just keep all the digits set to 0. Okay? A single digit in binary is known as a bit, or a binary digit, and you're going to hear this term from time to time. Just know that a bit, it's in either a 0 or a 1. Okay? If we want to represent 1, then we would do this. Okay, we would just put a 1 in the ones place. If we wanted to represent the decimal number we know is 2, what would we do? So we would need another bit. Okay, so we'll just add another bit and flip our 1 to a 0. Okay, so what about 3? Well, in decimal, if we had the number 10, what would we do to get to 11? We would just add 1 to the ones place. Okay, in binary, it's no different. To represent 3, we would just put 0, 1, 1. Okay, and 4, and 5, and 6, and 7. Okay, and now what would we need to do if we wanted to represent 8? Okay, exactly, we would need another bit. So 1, 0, 0, 0 would represent 8. So it would seem that with 3 bits we can count as high as 7, using 8 different orientations of these 0s and 1s. But counting as high as 7 isn't very helpful. It's not very useful. What would we do if we needed to represent a higher number, like 20,000? Well, we would need quite a few more bits. And just like decimal, with more bits, or more digits, we can represent an exponentially higher number. Okay, thankfully our computers have billions, trillions of transistors in them, and a transistor is like a microscopic light bulb in a sense. It can either be off, representing 0, or it can be on, representing a 1. And under the hood of your computer, that's what's actually happening. Okay, your transistors in your computer are storing a small amount of electricity, and that electricity can either be represented as a 0 or a 1. Now, typically 3 bits, or even 4 or 5 bits, isn't very useful, so we tend to group bits in groups of 8, and we call this a byte. Okay, you may have heard the term megabyte or gigabyte, and that's just what it sounds like, millions or billions of bytes that our computer is representing using these transistors. So that's all there is to binary, and with it, it seems we can count as high as we want as long as we have enough bits. But remember, computers are finite. We have a finite amount of memory and a finite amount of transistors. Granted, we have plenty to count to a number as high as we can imagine, but we cannot count to infinity, and that's an important concept to understand. Our computers will have run out of memory at some point. Okay? And if we scale this down just a bit to see what would happen, let's take our 3-bit example and say we count to 7 and we have 111, let's think about what would happen if we wanted to count to 8, but we didn't have another bit that we could add. So what would happen? Well, normally we would just flip the 3 ones to zeros and add another bit and set it to 1, and we would end up with 1000. Okay? But if we didn't have that bit and we flipped the 3 ones to zeros and that's it, then what we're really representing is the number 0. And the technical word for this is integer overflow, which has real-world implications. You might remember Y2K if you're old enough, and this was a problem that occurred when engineers realized that by only using 2 digits to represent the year, that when it changed from 1999 to the year 2000, our computers would think that we went from the year 1999 to the year 1900, and this would break things. Thankfully, we realized our mistake, and a lot of engineers were stuck fixing this bug in many softwares around the world. Okay, so we're actually going to be running into this problem again in the year 2038, because essentially computers start counting time from the year January 1st, 1970, and in the year 2038, the integers are going to overflow, and we're going to think it's the year 1970 all over again. Okay. Thankfully, we just throw hardware at this problem, and instead of using 32 bits to represent the integer for time, we're going to be using 64 bits to represent the integer for time. So this will extend our problem for many more years to come. Okay. So that's about it. I hope you learned a lot from this video. I hope you're comfortable with binary now. And just as an exercise, I'm going to give you 2 numbers in decimal that you should try to convert to binary, and 2 numbers in binary that you should try to convert to decimal. Just remember, there's a pattern in the numbers place. In decimal, we have the ones place, tens place, and hundreds place, and so on. In binary, we have the ones place, the twos place, the fours place, the eights place, and so on. Okay, so let's try to convert the number 208 into decimal. Or I'm sorry, from decimal into binary. Okay, pause the video, try to work this out on your own. Okay, so the answer is 1101,000. Okay, and we can check our work by adding up 128 plus 64 plus 16. And that's going to give us the number we know in decimal as 208. Okay, let's try another one. We have the decimal number 255. And again, pause the video, try to work out the math yourself. And here's the answer. We have 11111111. Okay, this is the decimal equivalent of 255. And you can do, again, check your math by adding up 128 plus 64 plus 32 plus 16 plus 8 plus 4 plus 2 and plus 1, and you should get the number 255. Okay, now what about if we need to go the opposite way? Okay, so what if we have this binary number and we want to convert it to decimal? Okay, well, it's the same thing. We have a place above each one of these numbers, and we just take that place and add it together to get the decimal number. Okay, so pause the video, try this on your own, and we'll be back in just a second with the answer. And there we have it. If we write the places right above the binary number, it makes it a lot easier. So we just add up 64 plus 16 plus 2, and we get the decimal number we know as 82. Okay, one more. So we have this number in binary. Okay, how would we convert this into decimal? Well, we would write the places above the binary number and then add up the digits. 128 plus 32 plus 1, and we get the number 161. Okay, try more of these on your own. Try converting random decimal numbers into binary, and then converting binary numbers into decimal, and see what you come up with. Thank you very much for watching, and I'll catch you in the next one.